Kia ora. This video here is a recording of the presentation that I did as part of the NZGrapher conference in 2026 in July. The recording is not perfect because there were a few times where I walked away from the microphone and that made it a little bit harder to hear. I'm sorry about that. I also forgot to start the recording at the start of the session. So I've recreated the first part of that, which was looking at the Display Explorer in the video here today. So without further ado, we will jump into that now. So we're going to start today having a look at the Display Explorer. So up the top here, we've got Display Explorer. This is great for kids to kind of get their head around the different types of displays and what's in the data. So we're going to click on that. And then we're presented with a couple of options. So the first one is the main variable I want to look at. Now for this one, I am looking at the Hoiho data, which is part of the 2026 extra data sets. So we're going to start off by looking at weight, because why not? So weight is a numerical variable, and that gives us a whole bunch of different graphs here of ways of displaying that data. All of these are clickable, so if I come and click on this one here, it brings it up in the big full view there, and I can jump back into the Display Explorer and then I can fiddle with some settings. So I can also come and have a look at an alternative variable. So I could have a look at weight and gender is a categorical variable. And we can see here there's various different ways of displaying that data. Again, all of these are clickable. If you click on any of them, it will open up that in the full view there as well. And we can come and also have a look at height, for example, which is a numerical variable, and it shows us the different types of graphs there. Or if I come back and just look at the gender, which is a categorical variable, it gives me some different ways of displaying that categorical variable. So I demonstrated that, and then I gave some time for people to have a bit of a play with that themselves before we jumped into the next bit. So I will go back at the end and re-record a thing on the Display Explorer for the people that are just joining us now on the recording. Yes?
Just a note, in terms of like the new level 3 that's being proposed, new level 3 stats, they've got a section in there about data exploration.
Yeah.
And so therefore this is where kids can start tapping into some of that. And that data exploration is also, I find, really good for my scholarship kids. So they see different graphs, and so they get the different representations of it.
Yeah, and oftentimes some of those graphs will show you absolutely nothing, and others will be really good at showing things. And so hence giving the kids the wide variety is quite good. So we're now going to come and have a look at the teaching tools. So if I left click rather than right click, in the teaching tools, we've got, we're not going to spend time looking at the video tutorials today, but if you want a video tutorial on how to use any of the teaching tools, there are video tutorials there that'll take you straight there. But we've got six now teaching tools that are trying to cover off the more complex, I don't know if complex is quite the right word, but particularly the newer bits of maths, the ones that aren't necessarily instantly intuitive. So the first one we're going to have a look at is we will do sampling variability, because this is probably the one that we do at the lowest end. So with this one, you can choose which graph you would like to do. So I'm going to do this on a dot plot, and we're going to come and grab our weight, and I'm going to put in a high box plot as well. So we've got the weight of our kiwis. We're going to pretend, not kiwis, Hoiho. We're going to pretend this is our population of Hoiho. It's not a population of Hoiho, but we're going to pretend it is. And what I'm going to do is I'm going to come in here with my pen, and I'm going to, on the whiteboard, draw my box and whisker plot. And then what we're going to do, so we know that that's our population. Or we're pretending it's our population. We can tell the kids it's the population. Then what I'm going to do is I'm going to do a simple random. Now I've only got 100 points here, so I'm going to take a simple random sample of 30. 30. And then I'm going to resample. So what I've done here is I've taken one sample of 30 penguins. And I can see my minimum has changed slightly, my lower quartile has definitely changed, the median has come down slightly, the upper quartile, and the maximum. Now what I'm going to do though, is I'm just going to reset that for a moment, is I'm going to lock the axis values. I forgot that when we started. Locking the axis values, what that does is it means that this always stays at 4, and this one always stays at 8, so as we're bringing the graphs up, it will not adjust them. So there we go, there's another sample that I've taken. We can see our minimums changed quite a bit, our maximums changed quite a bit, because there aren't, in the population, there weren't many at the min and the max. And we've got a little bit of change there in the middle. And what I can do is I can animate that. So I can go and say, cool, I'm going to take a whole bunch of samples of 30. So this is useful for kids to be thinking about what changes when we take samples. If there's 2 speeds, we can do fast or slow. So I'm going to actually speed it up a little bit, and we're going to kind of talk about the different points that we can see here. So we can see this bottom end, the minimum, is sort of going anywhere from here to here is our minimum. Same with our maximum. Our maximum sort of comes down, one of them came as far as there. Our maximum has that sort of variation in our samples. Whereas if we look at our median, the lowest median I think I've seen is about there, and the highest is about there. Yeah, it looks like it's generally staying inside that band. So we can see when we take a sample, the minimum that we get is probably not going to be a good representation of the population minimum, because it bounces around all over the place. Whereas the maximum, and same with the maximum is probably not going to necessarily be a true representation of the population, because it just takes one funny one to end up somewhere else. And whereas the median at a sample size of 30, we're getting an okay spread there. You know, it's probably going to be somewhere between 5.5 and 6. Now, what I can do now, though, is I can look at the effect of sample size. So rather than sampling 30, what happens if I up my sample to, say, 60? So now I'm taking a sample size of 60. And I can see my median now is sort of going from about here to about here. So this is a really visual way for the kids to see that as sample size increases, we're getting better representation of the population. Now, if I made this 80, given that we've only got a sample size of 100, that's going to shrink down even more. But likewise, if I did the other end of the scale, if I only took a sample of 10, we can see that that is all over the place. Particularly if I come and do just a box plot rather than a high box plot. We can see that that one is jumping all over the place. So the kids often ask, why do we do a sample size of 30? Because we often do sample sizes of 30. Any less than 30, it bounces around a really lot. More than 30, the bigger the sample, the better. But often taking a bigger sample takes longer, it's more expensive, particularly if you're actually doing something rather than making students traipse around and do things for you. 10 really is not a good sample, particularly for this data. The idea of this tool is it helps kids visually see what's happening when you're taking a sample. So I'm going to give you 2 minutes to have a play, and then we're going to jump onto the next teaching tool. Right. So the next one we're going to have a look at is the confidence interval coverage. So again, this is in the teaching tools and CI coverage. This is probably the next logical step up in terms of, what's the term I'm looking for here? In terms of where kids are at. So the sampling variability you can do from quite young. The confidence interval coverage teaching tool is more looking at the confidence intervals that we built for year 12. So this is looking at the range of data there. So what I've got here is I've got that same bit of data. So they're all 100 of them. Then we've got, we're going to take a sample and we're going to see what the confidence interval would be for that sample. So I'm going to just do 1. So here is a sample of 10. I can see that I've got a confidence interval that's about that wide for my median, and it plots it down the bottom. And so far, 100% of our confidence intervals have had the population median. Now, if I come and do this slowly, we can see that each sample we take, obviously, so at the moment we're just doing samples of 10. Each sample we take has quite a different confidence interval because we've got quite a small sample size. And we can see that over time, the blue ones contain the the population median, and the red ones don't. And so we can see that, over a long period of time, when we take a whole bunch of samples, at sample size 10, we're not super great, we should be ending up at about 90%. We're obviously a little bit lower than that in this one, but sample size 10 is not necessarily a great thing to do either. But we can also see what happens as we increase our sample size. So if I take my sample size instead of 10 and I make it 30, we can see our confidence intervals here have narrowed down quite significantly. In fact, I'm just going to reset that so that we can reset, and then we'll go medium speed this time. So we can see that's hitting about that 90% that we were expecting. It's obviously random, so you're going to get a little bit of variation, but we're getting much closer to that 90% coverage that we were expecting to see. And bearing in mind that this is just a rule of thumb, so it's not perfect. It's assuming that my original data is perfectly normally distributed, which we can see it's not. There's some other things going on in there. But it's kind of doing what you'd expect it to do on the tin. If we up our sample size to 50, we can see again those confidence intervals have narrowed down even more. So I'm going to give you just 2 minutes to have a play with this one as well. So that is teaching tools, CI coverage. Right. So taking that to the next step, the next thing, kind of as we work up the curriculum levels, we do once we hit year 13 is we start doing bootstrapping. Now bootstrapping is something that kind of came into the New Zealand curriculum in the 2013 curriculum refresh. Before that we didn't really do it. I really like bootstrapping because it gets rid of any of the assumptions that we make about the original data. We don't have to have normally distributed data. It works for whatever data you want to throw at it. The reason we didn't do it previously is it requires computing power to do. And so it's not, you can do it manually. Oftentimes depending on my class, I will get the kids to start doing a manual bootstrap. And then about halfway through, they'll get really bored, and we'll talk about why we use a computer instead. But what this tries to do is explain what is happening in the bootstrapping graphs. So if we're looking at this one, there is a video tutorial on how to use it as well. So you can find the bootstrap median or mean, but we're going to look at the median. We're going to start by taking one bootstrap sample. So I'm going to go slow. So what we're doing is we've got 100 points in our original data. And so what we're going to do is we're going to take a sample of 100 points here. But we're going to do that by pretending that this is a bag full of marbles with 100 marbles in it. We're going to pull one out, we're going to look at it, and then we're going to put it back in and shake it up. And then we're going to pull another one out, look at it, pop it back in, shake it up. So some points in here will get sampled more than once, and some of them will not get sampled at all. And because I'm getting bored, I'm going to speed that up. And that will eventually result in a sample. So we've got a bootstrap sample here. We've worked out the median of it, and we've plotted it down the bottom. What we want to do is we want to do that 1,000 times. So doing that by hand would be painful. Doing it by the computer isn't too bad. So I'm going to press the slow button, and we're going to get it going slowly to start off with. So what we can see here is in the middle we've got all of the different bootstrap samples, and they're being pulled down. The median for each one is being pulled down and put on the graph at the bottom. So we've done about 100 so far, but we want to do 1,000, so I'm going to speed that up so it gets done quicker. And then it's eventually going to finish. Right, so this gives us we can be reasonably confident at the back end of the population of all hoi-ho that the median weight will be somewhere between 5.6 and 6.1, if I'm rounding. What it does is it discards the lowest 25 medians, going, they're probably not going to happen, and it discards the highest 25 medians. Okay, so it cuts off those bottom ones, and it leaves you with that middle 950. So what we're saying is that there's a 95% chance, based on this, it's not exactly, that wording's not quite right. We can be 95, no, that's still not right. Does someone want to do that for me?
In the long run?
Yeah, in the long run.
95% with such confidence in it.
Such confidence intervals
I'm
would...
really salty about it, but I did level 3 in 2009. I'm a fairly young whippersnapper, and my teacher told me I had to write it like that, and I didn't listen to him, and I said 95% chance of my external and only got a merit. I'm still pretty salty.
So I wrote a program on my graphics calculator that answered one of the algebra questions in one of the externals. And I wrote the calculator program down as my working. I didn't get the excellence either.
Still turned out alright, Jack.
So did you, Michael, so did you. I'll let you have actually no, I'm going to jump on to the next one now as well. So this is doing a bootstrap for a single variable, but obviously once we get to year 13, we're wanting to look at the bootstrap for a difference. So we've got the bootstrap confidence interval teaching one, and I just want to reset that actually. Teaching tools, bootstrapping confidence interval. And we're going to look at weight by gender. I'm just going to zoom that out slightly because once it gets too small, things don't overlap properly. So what we're going to do with this one is exactly that same process. So we're going to do a bootstrap sample. I'm going to do it fast because we understand the process here. What we're doing is we're going into our bag, we're pulling one out, we're looking at not only the weight, but which category it goes in, and then we're putting it back in the bag. And we do that for however many points we've got in our sample, which in this case is 100. Then we work out the median of the two groups, we find the difference, and we plot that down the bottom. What we're going to do is we're going to do that 1,000 times. So we're working out the median for the females, the median for the males, and then we're plotting the difference on the graph down the bottom. So I'm going to do that fast now because we would like to go through all 1,000 of them. Now, you don't have to do this every time you want to produce a graph like this. We'll get to them in the graphs later on. In the same way that you don't, when you want to work out 36 times 72, you don't need to write out 72 36 times and then add them up. You can use a calculator for it. But if you don't understand what's happening with that multiplication, I wouldn't give the kid a calculator to do it. Same with, that's done some interesting things with the numbers. I will try and remember to do something about that at some point. So In this one that we've done here, if we were just using the main graph, it would just give us this at the end. And that's fine if the kids understand what's going on and behind it. The teaching tool is useful if you're trying to teach what's going on and behind it. So we've got here, in the population we had in our original sample we had a difference of 0.35. In our bootstrap sample, again, we've discarded the bottom 25 and the top 25. We're left with that middle 950. The difference between the weight, the female weights and the male weights in the population of all Kiwis is likely to be somewhere between negative 0.75 kilograms and 0.73 kilograms. If I say any of those phrasings slightly wrong, please jump in and correct me. Therefore, I cannot be confident that back in the population there is a difference in the median weights of male and female hoikos. Okay, because 0 is inside the confidence interval. Yes?
How many are there in the population? 100.
Previously we were using this data set as a population.
Yeah.
Now we're using it as a sample.
Right.
Just to be slightly
Are
confusing.
there even amounts of females and males? Like when you do this, the bootstrapping, are you...
It doesn't matter if there's an even number of males and females. Yeah.
I mean, like in the original was there? Or...
And the original was there? I don't know.
So when you do that, you're not worrying about, you might get more or less of each.
Correct.
It doesn't matter.
Yeah, no, it doesn't matter.
Okay.
And I think there was a reasonably similar number of males and females, but it may not have been exactly the same.
56 and 44.
There we go, 44 and 56. It doesn't work when one is very, very small, but as long as both are reasonable sizes, it works fine. So if you had like one at 10 and one at 90, that probably wouldn't work super well. But as long as you've got an okay number of them, it's okay. So that is the bootstrapping teaching tool, or the two bootstrapping teaching tools. Again, playing is good, so I want you to have a couple of minutes just playing, and then we will look at probably re-randomization. Cool, so the next one we're going to look at is re-randomization. Now, if I was clever, I would have a better data set in here for this. I don't have a good data set in here for this. So we're going to pretend. Are we all okay pretending? Yeah, okay. So we're going to pretend that this is some data from an experiment. So we're going to pretend that we've grabbed 100 males and 100 females from our class, and we have looked at their weights that they can easily lift up with their pinky finger. Okay, we're going to pretend. Okay, I know that's not what this data is, but we've got good imaginations. It's the end of the holidays. Our brains are freshly recharged. We can use our imaginations. So, what we're doing this time is we're coming to teaching tools, and we're coming to the re-randomization teaching tool. And what we're trying to do with this one, oh no, males and females wouldn't be good. No, what do I want? I want something else that we can control and randomize. Okay, I'm going to show you something else while we're here, and we're going to make some data up. So, in the sample and more, we have in the data, is it data? Yes, we have probability simulation. So we're going to make up some data. What we're going to have is we are going to have a couple of events. We are going to have the first outcome is the gender of the student, because I'm feeling particularly unimaginative today, just after I told you you've all got imaginations. And we can either have a male or a female, and we're going to say that there's a 0.5 probability for each of those to happen. And then I'm going to add another event, which is whether or not they get a ball in a box or not. Now they're going to do 5 throws. We'll do 5 throws. So we're going to call this one ball 1, and we're going to say whether or not it comes in the box or not. And we're going to say that probability is 0.5 and not in is going to be 0.5. And we're going to duplicate that because I want 5 balls. So ball 1, ball 2, ball 3, ball 4, and ball 5. And I am going to do a count of the number that end up in the box. Yeah, I'm going to slow down. So I'm going to zoom that in slightly more so you can see it. So I've come into data and gone into probability simulation. And what we've got here is the first one. I want to know whether or not the person is a boy or a girl, male or female. And then we're going to simulate this because I don't feel like doing the experiment, is we're going to have a box here. They're going to stand 3 meters away. They're going to have a screwed up piece of paper and I'm going to try and throw it in the box. And whether or not they get the first one in, the second one in, the third one in, the fourth one in, the fifth one in. And we're saying just for ease today that there is a 0.5 probability that for each of those shots that they get them in. And then what we're going to do is we're going to count up how many end up in the box. And then what you can do is you can choose how many trials you're going to do. So I'm going to do 30 because 30 sounds like a fun number to do. You could do 10. You could do 100. And you could play around and see what happens. That's the wonderful thing with simulations. I still didn't want males and females, did I? No, I didn't want males and females. I'm sorry. My brain is slowly catching up. We're not going to do males and females. We're going to have 1 meter and we're going to have 3 meters. Okay, so some of the people are throwing from 1 meter away and we're randomly choosing whether or not they're 1 meter away. And some of them are 3 meters away. And for the sake of our simulation today, we're going to pretend that both are just as good. But we're going to see what comes out in our data. There we go. Am I doing okay? Yeah, cool, awesome, thank you. Oh yes, I need to change the title. Thank you. Distance. There we go. Beautiful. Sorry, I woke up this morning with daggers in my throat and a fully blocked nose, and so I am drugged up, but we're getting there. So I now have a data set that looks like this. So I've got trial 1 through 30. I've got the distance that that person was away, either 1 meter or 3 meters, because we randomly put them in those groups. The number of times they got them in the box, and the count in the box. So now, if I come and have a look at my dot plot, looking at the distance, the count that they got in the box, and the distance away, and our summaries, we'll put on some box plots, we can see that the median for this one is 3 and the median for this one is 3. I would have liked it if we got a slightly different median. So what I can do is I can come into data, probability simulation, it's all right there, and I'm going to run it again and see if it gives me a better outcome. There we go, we've got different medians this time. So we got a median for the 1 meter of 3 and a median of the 3 meters of 2. Now, the question we need to ask is, did this happen by random chance, or did something, or did the distance cause that difference? So we're looking for that causal relationship. And because we controlled everything in our fictitious experiment that we did, how far the students were away, whether or not they were allowed to lean over when they were throwing or they had to stay standing up, whether or not they were throwing with their dominant hand or they're not, all of those other bits, the only bit that should have been changing, was the distance that they were away. But is it possible that a result like this could happen just by random chance? Let's find out. So this is where our re-randomization comes in. So we're going to come into the teaching tools and re-randomization. And in here, we can see in our original sample, the 3 meters was at 2 and the 1 meter was at 3. And so what we're going to do is we're going to take those 30 results that we had, and we're going to randomly put them either into a 1 metre group or a 3 metre group, just to see what would happen if they were put in those groups just by random chance. And the way we do that is we want to make sure we have the same original number that we had before. So the way I like to think about it with the students is if you've got a series of cards with the distance and the number of balls, we cut them all up, we shuffle them up and randomly put them down next to each other. So each one ends up, you get the same number in each group at the end, but each one is randomly in there. So what I'm going to do is I'm going to do one slowly. So what's happening here is it's finding each random point at the top, and it's choosing randomly whether or not to put it into the 1 metre group or the 3 metre group. And I'm going to run that fast because... Okay, so in our random count in the box, in that randomization, we ended up with a difference here of 1, so we've plotted it down the bottom. Now we're going to do this 1,000 times. So some of the time we're getting a difference of -1, some of the time we're getting a difference of 0, and some of the time we're getting a difference of 1. And what we find out is that a difference of 1 or more happens 36.1% of the time. So what we're saying here is that there's a 36% chance that this happened just by random chance. Now, this is where I like to discuss things with the kids about chance. If I told you that there was a 36% chance that if you walked out that door, you would get $1 million, who would go and walk out that door? Yeah, okay, you would 100% go and do it. If I told you that there was a 36% chance that if you went out that door, you would get mauled by a lion, how many of you are planning on walking out the door? So the context matters when you're thinking about this number. So in general, if that number is less than 5%, or sometimes we use P of 9, so less than 10%, and sometimes we use P of 1%. You know, it depends on which one you want to look at. And depending on what you're dealing with and the consequences, alters probably what number you'll want to look at. In general, we use, less than 5%, and everyone's happy with that. But if we were thinking about a trial of a new drug, if we found that there was, a 5% chance that the drug did nothing, but, there were no negative side effects of taking the drug, we'd probably go, cool, this is okay. Whereas if we found that there was a 5% chance of the drug having no effect, but half of the people that took the drug had really, really adverse side effects, that might alter how we view that number. And so I think there's a lot of nuance to these numbers that we want kids to be thinking about. So again, I'm going to give you just a minute or two to have a play, and then we will have a look at the last teaching tool that's in there. Right, so I'm going to do another probability simulation, just so that we can use that for our distribution tool. So I'm going to come in and, just because I could see a few people were not 100% sure about how that was done, so we're going to come into data and probability simulation. And what this lets us do is this lets us build a simulation of what might happen. Now, because I am feeling particularly uninventive today, we are going to roll 2 dice. I hope that's okay. So I'm going to call this one dice 1, and the possible outcomes I can get are 1, 2, 3, 4, 5, or 6, and because these are fair dice, I'm going to put in 1 out of 6 as my probability for each one of them. And then what I'm going to do is I'm going to duplicate that because I want to roll 2 dice. So I now have 2 dice. I've got 2 nicely theoretical dice. We've got their sides numbered 1 to 6, and they are perfectly fair dice. Because why would a dice not be perfectly fair? You could potentially simulate having an unfair dice if you would like. But I'm going to simulate having a fair dice. And what I'm going to do is I'm going to sum those together. So I'm going to look at what happens when I roll 1 and 2 dice, and what is the total of them together. I'm going to do 30, because again, 30 is a great number. It's not a perfect number, but it's a great number. So we're going to go 30. And then I'm going to press Create Dataset. I'll leave that up there for just a moment though, because I know some of you are still typing, because I was typing faster than you were. And I'm going to even this name. So, once we've got that, we press Create Dataset, and it gives us our 30 trials, the number that we got on our first dice, the number we got on our second dice, and the sum of those 2 dice. What I'm going to do now is I'm going to come into the teaching tools, and I'm going to go into simulation model. So, you must select a numerical variable for data, so I'm going to do that. Data is required. I'm going to choose the sum of the 2 dice. So, this is what my 30 looks like. Now, the cool thing with computers is if you're getting your kids to roll a couple of dice, rolling them 30 times and recording the results is probably about as many as you want to do. You can maybe get them up to 100. With the computer, you can do this 1,000 times or 10,000 times. Probably don't do more than that, it'll start lagging. But we've ended up with a distribution that looks like this. Now, theoretically, what would we expect our distribution to look like? What shape? Triangle, absolutely. We would expect it to look like a triangle. But it's not. So, we have not numeric continuous, we've got numeric whole number. And so then what we want to do is we want to look at what distributions could fit. So, our simulated distribution, we've tried with uniform, but uniform only works with continuous data. So we're going, and same with triangular and normal. So we'll try the Poisson. So what we're going to do is we're going to simulate what would happen if we were simulating a Poisson distribution. And we're going to do it 1,000 times. So that's a Poisson distribution. Oh, we're going to do it slowly to start off with. The red line is the current one, the grey lines in the background there, which are getting quite faint to see on the projector, are the different outcomes that we possibly could have got from the Poisson distribution. As I run that through, we can see that for a sample size of 30, we get quite a lot of variation. I'm going to do that a bit faster. And we can see the band of possible values there building up. So, based on our sample size of 30, we know it's not, we know it should be a triangular, but based on our sample size of 30, could this have been a Poisson distribution? Well, that looks fine, that looks fine, that looks fine, that looks fine. That one seems a little low, but it's still within the bounds of definite possibility. That's fine, that's fine. Again, this one seems a little bit low, still within the bounds of definite possibility though, and these are all fine. So could it have been a Poisson distribution behind it? Yeah, it could have. We only had a sample size of 30. Maybe it was a binomial. So let's run our binomial distribution. And looking at this, I think the binomial distribution is probably a little bit less likely probably than the Poisson, because down this end, this is never getting up to 2, and this one was never getting up to 3. Maybe it was an equally likely. So let me try an equally likely. I'm going to run that through fast. Could it have been that all of the outcomes were just equally likely to occur? Well, with a sample size of 30, yeah, it could be that they were all equally likely to occur. Now, what, however, would happen if I come in here and go data probability simulation, rather than doing 30 trials, let's do 1,000 trials. And now we'll come back into our simulation model and we will look at the sum. That's looking a little more triangular. Now, is it perfectly triangular? No, it's not perfectly triangular, but it's reasonably triangular. Now, we could say that actually this, we could pretend, because we like pretending in statistics, that this is a continuous distribution. It's not, but we could pretend. And then we could come along and go, well, what does that look like with a triangular distribution? And I'm going to say our min should be 2, our max should be 12, and our mode should actually be 7. Okay, you can update all of those numbers. And then we're going to run our simulation, and we're going to go, how well does our simulation match our data there? It's not perfect. It's close, but it's definitely not perfect. Yeah, so that is the simulation, what did we call it? That is a simulation model. So again, I'm just going to give you a couple of minutes to have a play, and then we're going to do a whirlwind tour through the different graph types. Right. So we're now going to have a bit of a whirlwind tour through the different graph types that are available on NZGrapher. Some of them will spend slightly longer on than others, but I also want to make sure that we have lunch at a reasonable time today as well. The first graph type that I really like, and it's first up in the list, is the pairs plot. So the pairs plot is again good for when students are exploring data. It gives you every single combination of pairs of data in the data set. So this one here, we've got gender, weight, height, and age. Weight, height, and age are all numerical. So they've given us nice little histograms of what that data looks like. Gender is categorical, so we can see the two different categories there. And then this one here is weight versus gender. This one would be gender versus height, and age versus gender. Whatever is here goes on that axis, whatever's there goes on that axis. And all of these are clickable. So, what I would never, of course, encourage a student to do when they were doing like bivariate data is go, well, which one of these has got a nice trend to talk about? Would never encourage them to do that, but I mean, you quite possibly would, because, yeah, so, age and height, you know, probably not going to be very good to write a statistical report on. Weight and height, you probably could. Height and gender, that looks quite interesting. Age and gender doesn't look particularly interesting. Now again, all of these, if you hover over them, they will tell you what it is, and if you click on it, it'll open it up. That nicely segues into dot plots and box and whiskers. So we are looking at the height of the hoiho by gender, and we're going to have a look at some of the different options that we've got under the graph. So summaries shows your summaries. Box plots puts the box down the bottom. Different people prefer the boxes in different places, which is why there is the high box plots. Sometimes you don't want to see the points at all, so you can hide the points. Sometimes a shape outline is useful. What this does is it kind of does some exponential smoothing in and around the data to work out roughly how high it feels like it should be. It's not perfect, but it's a way of visualizing the data, particularly when there's lots of points. Violin graphs. Basically does the same thing but puts them both top and bottom. The violin graphs go sideways because when I originally did them vertically I was told off. Bee swarm takes the points and just randomly distributes them around the middle. So it's just a different way of showing those things. Strip graph randomly puts the points anywhere inside the strip. When you've got quite large data sets, it can sort of help you see the density in there. Sometimes it's nice to see a box without the whiskers. Depends what you're trying to look at. Sometimes we like boxes without outliers. This particular data set doesn't have an outlier, but the rule for the outlier is if it is more than 1.5 times the interquartile range, less than the minimum or more than the maximum. Now, MAD. Who knows what MAD stands for? There we go. So rather than looking at the median, we can look at the mean absolute deviation. So this is kind of like the interquartile range, but it's based on the means rather than the medians. If you want to learn more about that, there's some cool stuff in Pip Arnold's book and also in the Gaze report. And you can show some numbers on there. We can also show the difference between the medians and the overall spread. So the blue line is your difference between the medians, which is one median and the other. The overall visual spread is your lower quartile to your upper quartile. And you can show some numbers on there as well, so that we can go, well, 3 out of 6.95 is a bit more than half. So yeah, there probably is a difference going on there. Then we've got the 1/2 and 3/4 rule. You can highlight some things. So you can highlight the top half and the bottom 3/4. You can highlight the bottom half and the top 3/4. We can see that they just overlap there. You can highlight the top 3/4 and the bottom half, and so on and so forth. We can see that those ones definitely don't overlap. So it's just some visual ways for the kids to see what's going on. And then we can get into the informal confidence intervals. So there's our informal confidence intervals that we'd want in year 12. The CI limits put the numbers at the end, and the highlight goes up and down so you can kind of more easily visually see if there is an overlap there. Point labels. Now, point labels used to be a lot more useful than they are now, because now you can just come and hover over any point and it will highlight it in the data set for you, which is probably nicer than the point labels, but sometimes the point labels are still useful. Mean dot. Put the dot in at the mean. Now, stack dots is the one that I get asked the most questions about. So, when I press stack dots, the graph suddenly looks really nice and pretty. When I unpress stack dots, it suddenly looks a bit messier. Now, if I take this point here as an example, I'm going to do my very best to draw exactly where it is. And then I tick the stack dots button, it jumps slightly to the left. Because the way the stack dots button works is it needs to put every dot into its own little column. So you can think of this as a super detailed histogram. That means that sometimes those points will be in the wrong place. They're not actually where the data is. They're pretty close to where the data is, but they're not exactly where the data is. So if I'm ticking that and unticking that, you can see that some of those points are shifting along slightly. Particularly if you look at these two towards the bottom of the bottom row, you can see one of them is moving quite a lot. So, stack dots is nice, it makes it look pretty, but it does make the data wrong. Does make it easier to see trends. So there are pros to it and there are cons to it, but sometimes when you don't have stack dots on, you get random little ones floating up here. That's floating up there because if it ended up down here, it would just be overlapping that point. So that's one of the questions I get asked probably the most. Grid lines, put some lines in. You can't see them on the projector, but I can see them on my screen. Invert colours. Didn't work. There's a fix out for that at the moment, but I haven't pushed it out to everyone. And thick lines just makes the lines of the dots just a little bit thicker, which is a bit fun. Point size. You can make the points bigger or smaller, depending on what you're wanting to do. Sometimes having little points is quite nice. Sometimes having big points is quite nice. You can have them filled in or not filled in. I like the filled in, but I understand sometimes you might not want them filled in. And you can also colour them. So I could colour them, and there's my gender's probably less useful, but I could colour them by age. And there I get a beautiful coloured graph. Now, while we're on colour, there is 2 colour schemes you can use. Rainbow is nice for the vast majority of people. Is anyone here colourblind though? I'm willing to admit that they're colourblind. That's all right. About 5% of the population are colourblind. Rainbow does not work very well for anyone that is colourblind, because they look at this and they cannot tell the difference between this dot here and this dot here. For most of us that have a full colour spectrum that we can see, we can really easily see the difference between those ones. But they would see them and they would be the same colour. So the other colour scheme that you've got in there is Viridis. So Viridis works for anyone that is colourblind, because not only does it have colour gradient, but it also has shading gradient. So we can see down here the 1 is very dark and the 20 is, that 20, wow, is very light. And so that also works nicely if you're going to be photocopying stuff in black and white or printing stuff in black and white, because it comes out with the various shades of colours. Down the bottom there is, so here we go, if I make that grayscale, you can still see the difference there in colours when it's grayscale. Showing ID of points removed, sometimes you will have a point like this one, which does not have a valid, I'm looking at gender. Let's look at age, there we go. Sometimes you'll get one where you don't have a valid point in there, and so it tells you which point has been removed. Point 69 has been removed. Yes?
Can you reverse those colours?
Can you reverse those colours? No, but it could be useful to have them reversed, eh? Do you want to flip me an email so I don't forget? Because I think that would be quite nice having them reversed. Cool, so that is dot plot, which is one of the ones that is used most often. We're just going to hit some of the key highlights today of the ones that are used most often. Bar graph and histogram I'm not going to go massively into today. They're quite useful for year 9s and 10s. Depending on what data set, maybe 11s, 12s and 13s as well, but slightly less useful. I like pie charts sometimes I don't. But we're going to look at scatter graphs. So we're going to look at weight and height because we're boring. Regression line, R value. Now R value is not ticked by default because at level 1, do we want the kids talking about R values? No, we don't. I like R values. I really like them. NZQA does not like them at level 1.
Doesn't even like them at level 3.
No. And they really don't like R squared values. So there is not an R squared value on there. You can work out your R squared value. Under sample and more advanced tools, it shows, I did not click on that, advanced tools, It can show you some of the information in there. There we go. Now it's decided. It's because I was way down. Yeah, cool. You can bring it up, and it'll show you the R squared value here in the console. But the calculator is reasonably straightforward as well. Point labels does what you expect. Mean dot. Now, mean dot is quite nice for year 11. Because any trend line should go through your mean dot. And mean dot is nice and easy for the kids to understand. Quadrant count. I'm not going to spend a lot of time today talking about the quadrant count and the quadrant count ratio. There has been enough discussion on the Facebook pages about that. It is a concept that the kids at a young age can understand that is not as mathematically computationally heavy as R value, and they can see exactly where it comes from. Is it perfect? No. Is it a thing that you can put in your tool belt? Yes. If you want to work out, learn more about where it's come from, there is some links on the info site to the Gaze report, which kind of talks about it in detail. Bootstrap trend line. I quite like this one. It's not at all in the curriculum, but I really like it. What this does is it takes 1,000 bootstrap samples, and for each one of them, plots a trend line. So you can go, based on that data, how confident am I in my trend? That one, well, the trend's reasonably stable. If I went and looked at age, there's pretty much no trend there. If you had a smaller sample, you're going to see more variation in those bootstrap trend lines. Jitter. Now, like I was talking about before with our dot plots and stacking dots, jitter moves the points around slightly. You can see it moving around slightly. It's really useful when you have a whole bunch of points that end up directly on top of each other. Jitter just sort of jitters them out slightly, so you can see actually there is a whole bunch of points there. You can fit all sorts of models on NZGrapher. None of these are required for the curriculum.
Really good for the scholarship stats.
They are really good for scholarship stats, and for these ones, if you want your R squared values, it gives them all to you in a nice little table in that extra tools. The emphasis should always be on what looks best. We were discussing this earlier. Every single one of these graphs here have the same R squared value. R squared is therefore not necessarily a perfect number. Is it really useful and do I really like it? Yes. But there are all sorts of nuances with it where we can see, all of these have got an R squared value of basically 0. But we can see that there's definitely trends going on in a bunch of them. R squared is not in the curriculum. Do I like it? Yes, I like it. Colour by distance. Let's get rid of that for a moment. What's happening there? Oh yeah, no, that is colouring it by distance. So what this is doing is, this is a really useful way to identify outliers or unusual points. What it does is it fits a series of ellipses based on the data and looks at the ones that are furthest away. So this one and this one are our most unusual points. This one up the top right here is also a little bit unusual. It's not unusual in that it's not on the trend line, but it is unusual that it's a long way from the center bobble of data. And so what you can do is you can also limit it and say, hey, I just want to color the worst one or the worst 5 or whatever that you'd like. Stack graphs. So if I split this by gender, I can look at my females and my males. Sometimes it's really nice to look at them overlaid on top of each other. So I can see how my females and my males compare to each other. So that's what the stack graphs does. Grid lines, fairly boring. Invert colors is currently broken. Thick lines makes things a bit thicker. You can also, and this is really, I'm going to unstack the graphs now. If you come to add a custom line, it gives you a couple of points on the graph that you can drag around. In fact, I'm going to get rid of the regression line. This is particularly useful for your year 11s. I'm going to, or younger, I'm going to tick that mean dot, if I can find it, there we go. So I know that my line needs to go through that mean dot. So I can drag these points around until it's going through the mean dot, and I can go, yeah, that looks about right. And then what I can also do is I can tick show equation, which shows the equation. You can add up to 3 lines on the graph. That is mainly for the physics students in year 13, because they, none of these are appropriate for that. But you can, if you're doing a physics experiment, you can get it to show the error bars. Residuals plot is one that I'm also asked questions about lots. People keep going. Can you change your x-axis? So the residuals plots fitted against residual. There is a tick box down the bottom here which changes the x-axis to the actual, what was on your x-axis. The reason by default it does fitted versus residuals is if they go on and do any further statistical stuff, it's always fitted versus residuals, because that's much better if you're doing anything non-linear. When we used to do stuff like Excel, though, we would often do the explanatory versus the residual. It's exactly the same, well, a slightly different scale, but for a linear model, it's kind of the same, but you can look at other models there as well.
Better to change it if you have a negative relationship. In other words, kids reading, you have to read the graph right to left.
Yes, yep. There we go. I knew there was a reason. Now, I'm not going to spend any time, because it's just about lunchtime, I'm not going to spend anything on the bootstrapping, the re-randomization. What that does is it basically, instead of having to step through all the processes, it just does them, boom, in one go. Paired experiment, I'm just going to quickly talk through the last ones and then we're going to have some lunch. The paired experiment is mainly for the level 2 experiments. It can do the arrow graph so that kids can see, do the arrows go this way, do the arrows go this way. And that's when you're looking at, if we were thinking about our experiment we did before, the same kid does it from 1 metre away and from 3 metres away, and you're looking at the difference between them. So that's your paired experiment data. Then there is time series graphs. I don't think I have any extra data here for the time series, so I'm going to quickly just show a couple of time series ones while we're here. Let's go for sea ice, because sea ice is fun. So, time series, the basic one, we'll do Antarctica, just shows you the data. There's a few different options. You can add the seasonal, that's pretty, isn't it? Lets you see the seasonal dots.
It's really good for level 1.
Yes. And long-term trend fits a long-term trend line. Oh, look, the amount of ice is going down. Shows you the seasonal, can give you the start and end numbers. Start and end numbers are not perfect to use, but they are a number. Grid lines, some. Now, additive versus multiplicative is the one thing that probably close to the last thing I'll talk about today. They are both useful depending on what you're looking at. Most things in economics follow a multiplicative model. However, the 2013 curriculum didn't really include multiplicative stuff in it. It only really talked about additive models. Because additive models are much easier to get your head around. You add or subtract the same amount each time. Multiplicative, same idea, but instead of adding and subtracting the same amount each time, you're multiplying or dividing by the same amount for each season. So if we think about economics, if I'm dealing with a budget of 100, I will have some seasonal variation, but it might sort of go up to 200 and down to 50. Whereas if I'm dealing with 100,000, it might go up to 200,000 and down to 50,000. So multiplicative adjusts that variation as you go higher, whereas additive, the variation stays the same as you go higher or lower. For the vast majority of data sets, there's not actually a huge difference there. Sometimes though, particularly for those kids, who are thinking about the excellence level stuff, getting them to, putting that multiplicative stuff in their toolkit is a good thing to do. And you can, again, add a custom line onto here. So you might want to come along and go, cool, what does this look like? And you can show the equation and it will work it out for you, which is quite nice. There is recomposition, which basically breaks it down into different parts. There is the seasonal effects, which just looks at the seasonal effects, which for sea ice data is quite nice to see that. Well, nice? That's the right word. It's pretty. You can see the change. And you've got forecasts as well. Now the forecasts, there is a doc on the info site if you want more details about how these work. The forecast model works on the Holt-Winters model. The other graphs are working on a seasonal trend low S decomposition. So there are different mathematical models underneath. Most of the time the kids don't need to know about that. It's just cool, what's happening in the future, what's happened in the past. But if you want to get into the weeds, I've tried to write a doc which is teacher friendly, but also for your top level kids friendly. It's not perfect, but if you've got suggestions on that, let me know. The forecast output just gives it to you as a table, and I've recently made it so that you can download that table as well. I think that was a Michael suggestion. Is that a Michael suggestion? Yeah. Yeah. Now, because those predictions are based on some randomization, if I update this graph, you will note that those numbers change slightly. The middle prediction numbers don't, but the actual prediction, but the range of values change a little bit because they're based off a process very similar to that bootstrapping, where it goes a little bit of randomization involved. So each time you generate it, you get slightly different numbers. This is useful for you as a teacher because if two kids have exactly the same minimum and maximum numbers, yes. Yes. So that is the time series stuff, and the last bit that I will do is in the help there is there's a whole bunch of bits in here. Some of them are better built out than others, but I'm working on them. There is the NZGrapher help site. So we've got dataset info, so the main datasets that are built in, as well as the extra ones from 25 and 26. Information on all the graphs, function information, which kind of talks about the different functions that are built in. Info on the school folders, info on how to make exam.net work slightly better. There's not as much NCA info as there used to be because it's all changed. And then there's also some video tutorials and teaching tools up there as well, which have a whole lot of video guides on most of the features, not all of them. I'm just building out a couple more at the moment, but things seem to constantly be changing, which makes things more complex. So that is pretty much us for this session.